Hello, students. This will be the second part of week 2, and I will do something. Now, let's recall what we in the first part. In the first part, we have introduced spherical coordinates, and then I let you see how to calculate that correction term. And spherical coordinates, if we choose the x, y, and z at a certain way, we can do by the x is r cosine phi, y is r sine phi. Then you have the, in certain sense, in the xy plane, the polar coordinates, and then we have some angle. You need some angle, and then we have done that by the cosine of theta, and then we have the other, the x and the y, you have to multiply by the sine of theta. And we introduced what we assumed was the radius is positive. The phi you can take between minus pi and pi, just if your interval of length 2 pi, no problem. And the theta we measured from the positive z-axis to beneath, and then you have only to take an interval of length alpha. If you do 2 alpha, you have the sphere on several, the whole sphere, you have two coordinates for the same point, and you have you want for every point of the sphere just one coordinate. And so we have here this is the sphere. We have this is the sphere, and then we have that correction term. Now we are in the RD phi is from the xy plane. Here we have some dimension x. We are in 3 dimensions, and so we have r squared, and then we have always times the cosine of the sine. I always forget which of the two it will be, but I think it will be the cosine, but I am not sure. So therefore I am now, no, it has to be the sine of theta. And then we have dr, d phi, d theta. So here we have all cases. Yes. I am asking myself, how can we why the sine? Now maybe we can see it as follows. You have the xy plane, of the xy plane, the three-dimensional space xyz, Cartesian coordinates, and just as I told you, in the xy plane we take the polar coordinates, and in the theta we measure from the positive z-axis. So here you have your theta, and what do you see if the theta becomes 0? If the theta is 0, you are measuring some, the different, if you make a little step in the r, phi, and theta direction, you measure what kind of step you make in with your volume. And if your theta is 0, you are at the z-axis, and what do you see? That you have that volume you have there. So you are so point here. You have the theta, and if that theta goes to 0, then the volume, that dv goes to 0. You have then in certain the dv goes to 0, and the the dv goes to 0, and so and that can only be done by the sine of theta. So you can look to it, and if you are in the xy plane, your phi is pi divided by 2, and then you have a volume, and that will be r squared. Okay. And if theta is 0, pi divided by 2, you are in certain sense, you are in the xy plane. Sorry, I will take some other color. And you are at this point here, and what do you have then? Then you have some r in the parallel to the x-axis, and you have some r parallel to the z-axis, and you have then here you have some area which is equal to r squared. So therefore, the sine of theta goes to 1 if the theta goes to pi divided by 2. So therefore, maybe this is a way to keep in mind for why if you have a sine of theta or the cosine of theta. But be careful, you have, it depends on how you choose your z variable. Okay, that is what that. Then we have the next step is in certain sense cylindrical coordinates. And then what do you have? Most of the time you have two variables, and there you can use just the polar coordinates. For instance, in the xy plane, that you can use r times the cosine of phi, y is r times the sine of phi, and then your z variable you does not change. That keeps you take equal to z, and then you have the cylindrical coordinates. And if you have then your dv, that's easy to remember because you have that step, the correction term of your polar coordinates, and in the z direction doesn't change anything, so you have 1 times z, so your dz is 1 times dz, and so your correction term here becomes r times the r d phi, and then dz. So that doesn't change anything, not so much. The only thing is that you have some extra dz term. So these come from the xy plane. Then I asked myself what to do with some with some hyperbole or something like that. A terrible thing from what to do here. What can we do then? So you have x squared plus y squared minus z squared is equal to r squared. And then, what to do then? That is, I was a little bit, I don't know. If what do we have? If z is equal to 0, I see that x squared plus y squared is equal to r squared. And so we have the following sketch. And you see I am always sketching figures, so just to see from how it goes, how it works. Now what do we have? If the radius of r is 0, you have a cone. So you have then something like this here. You have in the yz plane. Right? So if your x is 0, you have y is plus or minus z, and that you rotate around the z-axis. And here you have your cone. So that is the cone. And now, what did we see? If we took the z equal to 0, we have a circle in the xy plane. So we have this here. So if the r is not equal to 0, and we are sitting on this side of the cone. Sorry, I have to go through that point. R minus r, and then I can rotate everything around the z-axis, and I have my hyperbole. Yeah. Not an hyperbole, but a hyperboloid. And then how to parameterize. And so if the r not equal to 0. Now, because I took the z equal to 0 and I got some circle, I thought to myself the following, that if z is 0, we can maybe take x is r times the cosine of phi, and y is r times the sine of phi. And then if you have x squared plus y squared, you have r squared. That is nice, but that is only for the case z is 0. And yeah, with the cosine squared plus sine squared is 1, we don't do so much. Like the spherical coordinates we could take for the z variable, then something that doesn't work. But there is something else, and that is with the cosine hyperbolic and the sine hyperbolic. The cosine hyperbolic of phi, that's the exponential of phi plus the exponential of minus phi divided by 2. And the sine hyperbolic, e to the power phi minus e to the power minus phi divided by 2. They just look on that on the a little bit like the cosine and the sine with in complex numbers. And what do we know of this? If we take the squares of those of the cosine hyperbolic and we subtract the sine hyperbolic squared, if we subtract them from each other, we get 1 out of it. And so I think we can use that cosine hyperbolic and the sine hyperbolic because of this equation here. And just if you write out and see that is indeed the case. Now, and what can we then do? Now, if the phi is 0, I want to be in the xy plane. So I think that I can do then that I can take the z equal to r times the sine hyperbolic of phi. Now I have here I have written phi, but that is not so well. So let we change those phi's in some other. Let we give it some other name, and let we give it a name v. Let me do that. That is better to do because the phi looks like the angle in the xy plane, and that has nothing to do with it. Or let me say so, if we look to complex numbers, we can recognize something, but here we have something to do with. We have already a phi for the polar coordinates, so that here we do v. So and I think that we can do here sine of v. And so if the v is 0, your sine the z is 0. So I think that we can use this for our hyperboloid to parameterize. And so I have the suggestion to do the following. We take x, y, z. X we take equal to the cosine of phi and the y to the sine of phi. You saw that I took reasonable for the z to take the sine hyperbolic. Now, and if we have to do it this for the z, the sine hyperbolic, we can multiply the x and y by the cosine hyperbolic. Now, and we have now this here, and I think that we have we can use these for hyperboloids. And so if you have now x squared plus y squared minus z squared, if you calculate it, x squared plus y squared, that will give you r squared cosine hyperbolic squared, and then you have to subtract r squared and then the square of the sine hyperbolic, and we know that this becomes equal to r squared. So this goes well. This is a good parameterization for the hyperboloid. Then it satisfies this equation here, no problem. And then we have to calculate that that term, and or let me say, first of all, what can we take for our variables? Now, the radius we take greater than 0, no problem. The phi, let we take that between minus pi and pi, no problem. And the sine hyperbolic, a sketch of it. Sine hyperbolic, how in 0 it is 0, and if you take the derivative of it, of the sine hyperbolic, you get the cosine hyperbolic. So there it goes straight through the origin. So here you have a sketch of the sine hyperbolic. Let we have here v, and here we have the z, and here we have the graph of the z is equal to the sine hyperbolic of v. And this is just the graph of the sine hyperbolic. And you see that the z goes from minus infinity to plus infinity. So you have every z, or every element of r you have, that is no problem. And so you can take the z of the v you can take out of r. So here you have your boundaries of your variables, like the spherical coordinates. We have some boundaries. You have here also some boundaries for your variables of importance. And then you can calculate its I should say to you, calculate correction term. You know how to do it. Calculate the Jacobian. So take the derivatives, put them in a matrix, calculate the determinant, that is the Jacobian. And if you have the Jacobian, you have to take the absolute value of the Jacobian to get the correction term. But what shall we have here? Now, in the correction term of this will be the following. You will get the following, that the dv terms becomes equal to r squared, and then the cosine hyperbolic of v dr d phi, and then we have the dv. So here you see your correction term. Okay, that you can do yourself. There's a lot of work, but it's nice to do once. Then you know how you come to that correction term. So that's for hyperboloid. We make use of that cosine squared, the cosine hyperbolic squared minus sine hyperbolic squared is equal to 1. Now I think that this is enough. Then what I want to do is in the next video I like to do once more exercise 28 of chapter 14.5. I think that is nice to do. You have some idea. So correction term, let I write down. So calculate Jacobian. And the Jacobian, then you have the x in our case here, the x, the r, the x, the phi, the x, the v, and you do the same with those other variables. Here the y variable, you take also the partial derivatives to all those variables. You take the determinant of it, and that will be equal to the Jacobian. And if you are busy with some volume, you have to take the absolute value of your Jacobian. And times, in our case, dr, d phi, dv. And and here be careful, absolute value. And in our case, the cosine hyperbolic is always positive, so we have no problems with that. So these are the steps to do it. And then this will be the correction term. Okay, now I have done enough for this part.